Right, thank you for joining us for today's webinar with Tektronix and Electrorent. Before we begin, I just want to remind people who we are at Electrorent. At Electrorent, while we don't make the electronic testing equipment that engineers use, we do make it easier for organizations to procure and manage their test equipment. With an inventory of more than $1 billion and 11,000 product types, we carry test equipment from the top OEMs across the globe. Our global reach means that our inventory and our people are located where your people work. Electrorent provides end-to-end solutions for the complete test equipment lifecycle across many industries, including those you see on this screen. We're very lucky to have Bill and Satish from Tektronix presenting today. They both have extensive industry experience with power measurements. Combined, they have more than 38 years of Tektronix experience. Before I hand it over to Tektronix, please note if you do have any questions, to please put those in the chat. We will have a Q&A at the end of this session. Without further ado, Bill, let me hand over the presentation to you.
Thank you so much, Leon. And hopefully my slides are, I want to go over the agenda today. And so the topic is on mastering power measurements and modern power designs, and power is pretty general. So what we want to do in the first part is kind of define power electronics and talk about some trends in power electronics that are assuming are affecting you and your measurement designs today. So we want to then translate some of those trends into some of the measurement challenge that you're having, and then using an example of a switch mode power supply, because that is kind of the modern way we're measuring power today. I'll then hand it over to Satish. He's going to go into depth on the specific measurements for each phase within the switch mode power supply. And then we're going to end today with test system recommendations. What does that mean for your equipment? Probes, scopes, software, etc. Now, power electronics, pretty general topic. It's defined as, to generalize it, this diagram is showing that we have an input to a system. We need a source of power. And then we have a power converter stage, and then we have an output, really general. And the power converter stage is kind of in this middle box here, the integrated power systems. We have switch mode power supply, DC-DC regulator, and oftentimes a storage element, either a battery or a UPS. And again, this is highly generalized for the purpose of this. But power electronics is a branch of electrical engineering focused on the control and conversion of electrical power that often involves high currents and high voltages. And so as we enter 2025, there are clear, rapidly evolving trends shaping the power market. We want to talk about what is power electronics doing? What is it enabling in the market? So one that we're probably all familiar with is wide bandgap. Silicon carbide, gallium nitride. These materials are kind of taking over for silicon, and they're enabling the electrification of everything. You might have electric car, electric weed whacker and lawnmower. It's enabling this because they're able to deliver on higher efficiency, reduced heat dissipation, longer lifespan, and cost savings as it's helping us reduce our energy consumption. Next is power management. This is that middle box that we previously showed that's used to convert, control, monitor, and distribute power. There's chips that make up this set in some circuit boards that we call power management ICs or PMICs. And these management systems are used in many applications, including automotive, consumer, industrial, communications, data center, computing, and medical. So pretty wide. And the next is the motor drive market. As we just use electric vehicles as an example, one reason this is a pretty big trend and what it's enabling is more efficiency. So 45 to 50% of the world's electricity is consumed by motors, pretty staggering stat. And it's used by industrial motors, industrial machinery, HVAC systems, heat pumps, and compressors and generators. So by developing efficient motors, we can reduce the energy consumption, lower greenhouse gases, save on energy costs, and reduce audible noise. These new designs are helping improve EV performance on the motors and trucks as well. So what this means for you is now your range is not 250 miles, it's 300. You can now hit that next charging station. Really good benefits for us consumers. And the last is the battery and energy storage. There's currently 2.2 terawatt hours per year of commissioned lithium-ion battery manufacturing capacity global. It's double the capacity that existed 2 years ago, which is 4 times the capacity of 2020. This is really booming. E-mobility and handheld systems and battery energy systems, storage systems will drive this growth for the next 10 years. So when we keep giving this webinar, we're probably going to have higher stats. Batteries are going to continue to be part of the story of what's getting enabled in this power electronics market. Next, we want to talk about, so this growth is leading to some trends, and these trends are therefore turning into challenges for you as design engineers in the power system. Before I talk about this, Leon's going to show a quick polling question to get an idea of some trends that are affecting you today.
All right, let me go in here and launch this poll. Yeah, we're looking at meeting EMI EMC compliance is definitely the top answer here with 80%. Some 60-40-20 on the others, but EMI and EMC compliance are definitely the top pain point.
Thanks, Leon, and thanks for answering the questions. That's interesting. EMI EMC is, we're not planning to go very deep on that today, but good to know, and maybe a topic for a future webinar. So as we talked about, silicon carbide and gallium nitride are driving a lot of new test trends to help us improve reliability and efficiency. Fun fact, and this is maybe my Wikipedia that you can fact check me, but it looks like the first switch mode power supply, it looks like it's invented before around 1950-ish, but it looks like IBM had deployed one in 1958 and it was used by NASA. And it makes a lot of sense because I guess there were linear power supplies before, and they needed, basically the request is what happens today. There's a need and it drives innovation. Needed something smaller, lighter, and more efficient. You'd imagine you want to get something up in space. That's important. So that market demand drove the innovation, and that still continues today with the trends that we just mentioned before. So I think it's pretty obvious, based on those trends we just talked about, the increased efficiency is needed for the motors to keep our power consumption lower. The higher power density, we want to get more in a package, and the transient loads. You know, we have to handle changes in load conditions. The topologies and multiple outputs is quite a challenge, and the ability to, the reason we're looking at silicon carbide and gallium nitride, first of all, it helps us switch faster, but at higher voltages to get some of that current down, but we're also seeing higher currents. Okay, so most in the audience today, I assume, are on the right side. Okay, that's what we want to understand. Which of these are the most challenging for you? Because all of them are going to give you challenges on how you are measuring power or designing measured power today. So increased accuracy with all these present, with higher voltages, faster loads, etc. That's an important part of your measurement system. The safety and probing, which we'll talk about, stability testing, EMI, EMC, which we talked about, faster switching, more emissions, how do we keep that in check? And then the dynamic range and higher voltage, faster switching speeds are all key elements that are critical in the measurement system. I want to frame up what we're going to talk about today. So, you know, who's this for and what we're going to talk about. So this is, again, the generalized power system. We're going to focus on what's in that box. We're going to look at the example of a AC/DC switch mode power supply. And we're going to look at the challenges of putting this in your system. If you're designing them or you're deploying them, what are the elements of it and what are the potential issues that could cause downstream in your design? The most common architecture is going to be the switch mode power supply. So in this block diagram, this architecture minimizes the use of lossy components. Instead, it uses switch mode semiconductor devices and magnetic and passive components, which are ideally lossless. So this high-level diagram is going to generalize the portion. So first we have an input portion, the switch. The switch is going to go to the transformer and the filter, and then there's a feedback loop with the controlled circuit. So I want to talk real briefly just about what these are, and this will help frame up Satish's section about the measurements for each. So in the input section, it takes the high voltage AC signal and converts it to high voltage DC. It uses rectifiers and filters in the input section. That high voltage DC then gets sent to the switch. and that DC is converted into high voltage pulse streams using various FETs. And then the transformer section brings that down to the required voltages. And the final section, we have the output rectifier and filter, which converts these square pulses into DC levels. And we also have the control circuit, which monitors and controls any variations in the required DC output. Switch mode power supplies typically include a control section because of the various waveforms, especially with dynamic loads, et cetera, that it has to accommodate. As you followed along with those sections, the AC waveforms, as you can see, kind of what that looks like through the stages, is it converts to a DC with some ripple through the rectifiers, then through the switch, and then ultimately DC out. The reason I want to go through those stages is because how Satish is framing up his measurements, there's specific measurements that are specific to each stage of that power conversion. Before I go into these real quick, Leon's got another polling question for the audience.
All right, let me launch a poll here on some critical measurements, and the poll is now open. 75% here say all of these are equally important. We also did have 50% at efficiency as well. So
that's very helpful. Thank you. I would have guessed efficiency. I wasn't sure what I would expect if most of the engineers look at this as a black box and look at the input output, or if they're actually in the individual stages. So what we wanted to highlight are the measurements in each stage are what you would consider. What we're going to talk about today, because we have limited time, are the measurements in bold. And so don't want to take up more time, and I'd like to introduce Satish, who's going to help you understand how to, for example, make the harmonics and power quality inrush current measurements and input capacitance at the input side. Switching loss measurements are probably one of the most important, as well as ripple on the output. And then if you are getting into the magnetics and the transformer, what are some of the measurements that we can perform there as well? So I'd like to now turn it over to Satish, who's going to talk about the measurements for each of the input stages.
All right, thanks, Will. Hello, everybody. So I would like to take some time to talk about some of the key measurements which Bill was actually introducing on some of these sections of the switch mode power supply. So let's start from the different blocks. On the top, you see the input block here. So that's like an input rectifier block. So that's where I think we will do the power quality measurements. That's one of the important measurement here. Basically looking at the inline AC voltage. So it can be like around 110 volts in many countries, and it can go up to like 220 or 230 volts in other countries as well. So it consists of input filter, a rectifier section which converts the AC signal into an high voltage DC, and it's very important to measure the characteristics of the signal to understand the power and also the many power factors of the input side. So for doing this, we have to capture both the voltage and current waveforms from the input section with appropriate probes. We will talk about which probes to be used and how do we capture that in the later section. And so we will actually do a power waveform calculation. So power is nothing but the simple multiplication of voltage and current. And so since there are many inductive and capacitive components which are present in the input section, so the current and voltage will not be the same phase, and there'll be same phase difference between them, and that contributes to this power triangle. So you will actually have an active power, which is actually the power which is delivered to the load, and there'll be something called as a reactive power, which doesn't get delivered to the load, but it gets keeps oscillating between the power supply, I mean the input side, and the and in the active components like capacitors and inductors. And so we want to reduce that part. And so the apparent power is nothing but how much is the power dissipation looks like. So that's the resultant of both of these. So we would be mainly interested at looking at many things here, like what is the instantaneous power at a particular instance of time, and what's the true power which is actually being consumed by the loads, and what is the reactive power which is actually going back and forth from the source and the load, and which doesn't get consumed. And yeah, and there are other factors like the crest factor, and also for voltage and current, and also we'll be looking at the RMS values of these current and voltages. So these are pretty important basic measurements for the input section. So which is yeah, we can do it manually also, but nowadays most of the scopes, I think many of the scopes have this as part of the standard measurement package. So if you go to the next slide, Bill, we have our software which shows all these measurements automatically finding out with the waveforms. You can see the channel 1 and channel 3 are the voltage and current waveforms, and the math one is the power waveform, and there's an energy waveform computed also, and you get to see all the power quality measurements listed here. So this is something which is can be done automatically, and you get to see a lot of insights into the power quality. So next, I will talk about the next measurement, which is harmonics. Again, basically harmonic refers to the distortions in voltage and current waveforms. So typically it is caused by nonlinear loads which are present in the SMPS, and the input current is often which will be pulse width modulated in the next section, like the switching section, and that will actually cause the non-linearities, and that will actually add a lot of distortion back to the mains, and that can actually potentially disturb the other instruments or the equipments which are present in the equipment, in the circuit. So that's why it's very important to measure the harmonics and make sure that harmonics is not exceeding any of the limits. So basically, why do we need to? Why does it matter? So if you don't care about harmonics, what actually happens? So basically, there are many things which can actually happen. So it can reduce the system efficiency. It can also cause overheating of the device, and it can also cause many times it can cause failures in the field. So we need to make sure we don't have the harmonics components above the range. So there are many standards which are actually there to define how much is the harmonic contents needs to be like. So there is a standard called IEEE 61000-3-2, which has different classes depending on the type of SMPS circuit. So, and it defines up to 40th harmonic how much should be the limit for each harmonic component. And you can actually see that we can it's a frequency-based measurement, so we get to see the frequency domain. You need to do the FFT on the scope on both current and voltage waveforms, and try to see that frequency component up to the specific order. Yeah, these things again can be done with a standard measurement in the scope. And here you can see that I have an harmonic component up to 40th order, and it shows what is my limit and what is the harmonic value, and whether it's passing or failing. So since it's all green, so I would say it's pass, and it's meeting my specification. And I would see the margin as well, how much margin I have for each harmonic component. So, and this is very important to measure for people who are actually characterizing their input section. Along with IEC, we also have many other standards, and many people would like to look at custom standards as well, which are evolving right now. And also they would also want to measure up to more than 40th harmonic as well. So which is also possible with the scopes. Yeah, so other important measurements for input section are like inrush current. So inrush current is nothing but the initial surge of current which is drawn by the power supply when it's first powered on, and this surge occurs as the input capacitors charge rapidly, and often drawing 5 to 10 times more current than the normal operating current. So if the input current is not managed properly, it can actually trip the circuit and cause failures. It can blow up the fuses, and it can also add stress to the other components, and it can reduce the lifespan of the overall system. So it's important to accurately measure the inrush current and uh, add properly rated fuses and protection devices, and also ensuring the power supply reliability. So it's again important to measure this current. So so we can actually do this measurement manually by placing cursors on the scope, and also we have an inbuilt measurement which can actually just do it where it will guide you through certain steps, and it will just capture the signal and do this how much is the inrush current. And again, the next important thing is again how much is the input capacitance. So which actually which is a measure of how much is the charge which is drawn at startup of the SMPS circuit, and it also influences the inrush current profile as well. So again, measuring this is also very important to find out the startup behavior and model that accurately. And you can also design soft start circuits as well to prevent these effects. And you can also optimize. There can be some EMI effects because of this. So you can, which is very important to optimize. So by knowing the behavior of these things like inrush current and capacitance, we can actually optimize the EMI filters as well. So this is about the input section. So now I will talk about some of the important measurements, especially on the switching. So we have the next block, which is actually switching devices, which will actually switch the switch the input and convert the DC to an pulsating AC kind of signal. So we have a pulse width modulated AC signal out of this. And so we will actually basically the switching is very important to measure how much is the losses because of the switching. So there'll be turn on, turn off losses, and also there'll be conduction loss, which is the loss which is actually happening when the switch is on. And today's modern devices actually are very efficient. So the switches are like, I would say, we are looking at my efficiency is more than 90%, and these losses would be like very low, and especially for higher switching speeds. Again, measuring these very small losses is it's not very easy. So that's why you need to have a dedicated instrument which actually can capture these signals accurately with a higher sample rates and higher bandwidth to see these edges, switching transitions, and make these measurements accurately. We also see the graphical plot of switching regions, how actually the switching happens. So that's again important to find out the characteristics of the switching. And a couple of tips when you are actually making these measurements. So it's very important to maintain proper doing proper DSQ between voltage and current signals. So you should make sure they are both aligned in time. Otherwise, you might end up measuring some values which are not correct. So we look at how do we do that? How do we do proper DSQ before we take these measurements towards the end? And we need to also make sure the proper probe compensation, and we have short ground leads to reduce ringing and noise. And having an automated measurement tools will actually improve repeatability, like we are seeing right now. So that can have a repeatable measurement, reducing the human errors, because a lot of times if you do it manually, you might end up putting the cursors at a wrong place, but it takes a lot of time also. So having an automated measurements is very important for making these measurements. Yeah, so why do you need to really measure switching characteristics? Basically, you have to achieve higher efficiencies, especially today's designs need more than 90% or like close to 100% is what they are looking at. So that's where I think we need to properly measure the switching losses and characterize that. And you can also reduce lower heat generation. So by looking at how much is the loss, I think that will help us to design the circuit such that will reduce the uh, heat generation, and also we don't need to have an bigger heat sinks to dissipate that heat. So similarly, the next measurement is something like a safe operating area. So this is a very interesting measurement, which is a plot of voltage versus current. So that characterizes the operating region of the switching device. So usually under diverse operating conditions, so power supply is expected to encounter different operating regions. So we'll find out the operating region with this method. So there's an mask, so which will actually get superimposed on the plot, and you will see the switching device specification limits, and also you will see whether your transitions are actually hitting the mask or not. So you have the safe, your device is in the safe operating area or not. So basically, especially it's important to measure the safe operating area to look at the startup and the load transients, and also there can be short circuit conditions, which can be characterized by looking at the safe operating area measurement. So with oscilloscopes, using the SOA mask, we can actually define acceptable voltage and current boundaries. So during switching events, so oscilloscope actually checks if the transition, if the waveform actually hits the mask or not. So if there are violations and if it is hitting the mask, so then it means that it's out of the operating region. So this actually again helps in validation of the designs, and also make sure so we have a reliable testing done. Before we actually go to the next step of manufacturing. So having spoken about switching devices now, I think it's very important to look at magnetics, which many people don't know whether that's so important. Actually, it is. So why does it really matter? So basically, we need to characterize the transformers and inductors, so which are actually kind of hard for the SLPS circuits, and their behavior impacts the efficiency and also EMI performance and also the thermal characteristics of the SLPS device. And so unlike electrical parameters, so magnetic properties are like non-linear and frequency dependent. So it's actually harder to characterize them. So without specialized tools. So that's why. So we have some of the specialized tools in the oscilloscope to capture basically the voltage and current across this magnetizing coils, and then by using number of turns and the total magnetic path length and the cross section area, so we can actually get a nice BH curve to look at the maximum flux density and also the permeability, and also there are many losses actually which you will find out from this plot. So you will either find out whether you're actually hitting the saturation during this from the power conversion stage, and also by looking at the BH curve, you will actually get to know a lot of other characteristics of the device. So a couple of things which we need to note down here is like the losses which are important is like the core loss and the copper loss. So the core loss can be a datasheet parameter, or you can actually find out that from the BH curve here. And the copper loss, it can be derived from current and also the winding resistance. So we have a dedicated measurement to perform the measurement, the BH curve, and also the look at the I versus integration of V curve, and also the inductance curve. So these are some key parameters actually when you're looking at magnetic analysis. Well, so we have spoken about the first three stages. So now the last stage, the important measurement for the last stage, which is ripple. So the output measurement section, basically like when you have an SNPS circuit, so you need to have, let's say if you are converting an AC to DC, and you want to have an as stable DC power as much as possible. So that's why, but it is not in the real world. It is not. It won't be uh, as clean as we wanted. So there will be a ripple, which will be an AC signal superimposed on the DC power supply output. So we need to measure that ripple and characterize that and see whether that is not affecting my actual circuit after that. So basically you have to you need to have very high accuracy, accurate probes and a testing system to measure that. Because it's not very easy because it will be in the level of it can be in the level of millivolts or microvolts depending on which kind of circuit you're working on. So accurately measuring that is a challenge. Uh, so we will actually talk about how we can actually measure that accurately and see more into microvolts level of ripple. A couple of things on how do you measure that ripple well. So that's something like you need to have a very good a low noise differential probe or a passive probe with short ground leads, and you need to make the scope into an AC coupling mode to isolate the DC level because the DC level can be beyond the uh, measuring range of the scope. So you will be looking at the AC component of the power rail. And sometimes you might have to reduce the bandwidth of the scope to avoid high frequency noise and just look at the region, I mean the frequencies of interest. And you might need to zoom into the ripple waveform and look into that for better resolution. So there are various methods to do this, and we also have a specialized probe to do that. So called as power rail probe. That's something which is an best probe, which has a very good sensitivity, and you can actually look at the micro volt range of ripple, which is very common in today's switching devices. So a couple of things to look at ripple is like, so what is my peak to peak value of ripple? What is the RMS value of ripple? And at which frequencies is this ripple is present? And measuring that, I think that gives us a lot of ideas about our output section, and we can actually optimize that by looking at these values. Other than ripple, so I think the most important measurement here is the efficiency of the power supply. So again, efficiency is a key performance metric that reflects how effectively a power supply converts the input power to the usable output power. So it actually impacts a lot of things, especially the thermal performance. So if it is not efficient, so there'll be a lot of thermal losses as per in the form of heat. And also we can get to know the energy consumption statistics as well. And we also have system reliability metrics which will be defined by the efficiency standards. And there are many standards for efficiencies as well, so which many people wants to comply with. So we can actually measure the efficiencies for an AC-DC, DC-DC, or DC-AC, or even for an AC-AC converters as well. We just need to probe across the input side to capture both voltage and current on the input side and also the output side. And you can also have one input or multiple outputs. So when you have multiple outputs, the the total output power is sum of all the powers of all the all the outputs. And so you measure the power on the input side and measure the power on the output side, and that you divide the output power input power by the input power, and you will get to know the efficiency. So it's a simple measurement, but you need to have and good equipment to capture these signals and measure this very accurately. So you need to have a good resolution in the scope to make this measurement very accurately. So even a small improvement in the efficiency can lead to a lot of advantages for the SLPS designer, because he doesn't need to worry about heat sinks, so to dissipate that heat, and it also saves a lot of money when you are actually saving that. When you're having a very efficient systems. So this is again very important measurement. A lot of people actually, I think, as we see in the poll as well. So this is one of the very important measurement for the power supply design engineers. So now, though we looked at the key measurements which are actually to be done during the SLPS design and validation. So now I will hand it over back to Bill to talk about how do we actually capture the signal, and there are many recommendations for the test system to do all these measurements.
Thanks, Satish. There's a lot to cover. Clearly, you didn't even hit on all of the measurements to make, but as you said, these are the key measurements. And so for this portion, we just want to talk about the test recommendations. So to get these accurate measurements and to handle these voltage and currents, you need multiple components for your test system. So first of all, you need the right oscilloscope. You need the right digitizing device to be able to capture these waveforms at high enough resolution. Next, for many of the measurements, you're going to need voltage and current probes. And so we'll just have a quick highlight of what's needed. And the last part is the software. So Satish was showing some screenshots. So we just want to give you an idea of how he created those and what enables our measurements within our oscilloscope. First of all, let's talk about the key portion of the measurement system, which is going to be the oscilloscope or the digitizer. And conventional test systems for measuring power consist of multiple instruments. Maybe before these were digital or had, as we like to say, 3, 4, 5 instruments in one, you would have an oscilloscope. You would often have to resort to frequency domain analysis and have a spectrum analyzer. You need a function generator, an LCR meter, impedance analyzer, a vector network analyzer, and sometimes a response, frequency response analyzer. What is great about the modernization of oscilloscopes is a lot of these components have been built in to the oscilloscope, and some of them are actually, different hardware devices. So for example, on what I'm referring to here is the MSO 4, 5, and 6B series from Tektronix. They have a separate arbitrary waveform generator or function generator built in on the back. So it's different hardware that can generate these output signals. We also have what we call spectrum view, which is a different signal path which gets down converted and gives you a spectrum view of the time domain signal. And so these are now built in, which is greatly simplifying your job as an engineer. It's going to be hard to go over all the options for the oscilloscopes, but what I want to leave you with is, as we recommended the 4, 5, or 6 series, some key things to think about within your measurements. Do you have enough bandwidth? For power signals, you're generally not going to have really high slew rates. So 10 gigahertz is probably overkill, but what you want to pay attention to if you're making harmonics measurements, if you're making the 40th harmonic, do you have enough bandwidth to be able to accurately capture that? So bandwidth is going to be the first consideration. Clearly the number of channels. If you're making efficiency measurements, that might be one of the most taxing on channel inputs if you have multiple phases, because now you need a channel per voltage and current. And if you're doing 3 phases, there's 6 just on an input or output side. And so the Tektronix oscilloscopes have different flavors of 4, 6, and 8 channels. And we can actually stack them or combine them to get 16. So if that's of interest, you can reach out to your sales team. Accuracy was another challenge. How do we get more accuracy within our measurements? And so within your measurement system, you have to look at not only the scope, but the probes. But to start, within your digitizing system, we have a 12-bit ADC. And so that's going to give you a lot better resolution within your measurements, DC, AC, et cetera. So that's a key component when you choose your measurement system. And last, sample rate. There's some rules of thumb, maybe 10x times your primary fundamental but it's 6.5 gigasamples per second on the 4 and 5 series, and then up to 50 gigasamples on your 6 series. So some things to consider when you're choosing your digitizer system. Next is probing. Satish kind of glossed over some of this within the measurements because we didn't have enough time to say here's where we're making the probing points and here's the probes to recommend, because with each measurement there's actually not one probe that makes them all well. It's going to be specific per measurement. And so one takeaway is a passive probe is a great tool because they're relatively inexpensive. They have high voltage ratings, sometimes up to 500 volts, and they have good proper CAT ratings when you're working with power. And they can be used for most single-ended measurements. They're not differential. So if you need that, one of the popular tools is going to be the high voltage differential probe. You're going to be safe up to maybe Cat 3. Some of them are rated differentially up to 6 kilovolts. And then for current, many different methods here. One of our most populars are Hall effects, which we call our TCP, or Rogowski current probes, which will give you less bandwidth but higher current rating. And Satish also did mention the importance of D-skew. If you're measuring power, you have to understand that's voltages times current. And when you have slight skew within those measurements, and every oscilloscope, every signal path is going to have some skew. A lot of that's accommodated when you plug in the probe, but you want to make sure that that D-skew is taken care of. So just a couple ideas on voltage probes. The high voltage differential, which we call THDP or TMDP. We have up to 200 megahertz and ratings up to 6 kV, both common mode and differential. We do have some isolated probes that are up to 1 gigahertz. They're significantly higher in a common mode voltage, up to 60 kV, and differentially at 2.5 kV. And then our passive probes, as we mentioned, we have passive probes that are now, used to be 500 was the max. We have new innovative TPP probes up to 1 gigahertz with pretty low loading. And that shouldn't be differential voltage there, but single-ended voltage will be up to 2.5 kV. A point on the isolated probes, when you're debugging some problems that could potentially be due to ground loop, ground bounce, etc., the isolated probes have true galvanic isolation. On our voltage probe here, it uses optical isolation. And I'm going to talk about current probes here. This is another isolated probe, which has RF true galvanic isolation. And so an option for current probes would be a Rogowski. We have them up to 30 megahertz. We have a new TICP, which is an isolated current shunt probe up to 1 gigahertz, and then our TCP up to 120 megahertz. Our website has all the options here, and we'd be happy to help you understand which one is best for your measurement system. The D-skew, we have that signal source, which I referenced, and then there's also a fixture. This fixture is great because you can hook up multiple probes to that fixture, so the signal's arriving at the same time per the channel, and so there's actually a procedure within the scope that can actually take care of this for you, or you can do it yourself manually. And probably the star of the show is the software. You got to saw a lot of the screenshots, but not really sure how these measurements were made. How we enable these, there's a software option that's enabled on your oscilloscope. It's called 4, depends on the scope. If you choose a 4 series, it's 4-PWR, 5 or 6-PWR. And this is showing you a lot of these waveforms that are integrated, measurements that are integrated into the scope. So why is this important? You used to have to make measurements with cursors or eyeballing and counting graticles. We have built these measurements into the oscilloscope so it makes them automatically. You can see the measurements listed here. It was too hard to show all the menus expanded. So for timing analysis, magnetic analysis, etc., the ones that Satish mentioned are all here. What's also interesting and helpful for the engineer is we have ways to annotate. You can maybe say, yeah, I don't trust the scope. It's making these measurements. I trust me doing it myself. We can turn on where the measurement's being made. And if you don't agree or that doesn't meet your company's standards or something, you can actually adjust that and make it yourself. But it does tell you where the measurement's being made, so it's transparent if that's a concern. So to summarize, we've talked about the changes in power electronics and how it's enabled a lot of innovation in our space, but it's creating trends of higher density and faster switching and greater efficiency. These all translate into increased measurement complexity. It makes your job harder. Not often designs aren't designed for test. And so on the test side, you need to figure out, how do I measure the switching loss, magnetic behavior, ripple, and compliance, et cetera. And so we have taken on that burden, integrated these tools into our instruments to make your life easier. And the automated measurement portion of building these measurements into the system, make sure that your measurements are repeatable. So you could make the measurement one day, hand it to a colleague, and you should be able to get the same measurement, where if you were doing it manually, the repeatability is going to suffer. And because they're built in, we have automation tools that can actually do this for you if you're doing automated measurements as well. So you leave your test setup, hit go, and it runs. And the last part, we just want to make sure we emphasize the importance of proper probing. That is the last mile of your measurement, literally your last couple inches. If you take that for granted and you use inferior probing, your measurement is going to suffer. It's going to suffer in accuracies. And if you have the wrong frequent bandwidth, it's going to change your slew rate. It's not going to give you the measurement that your system is actually seeing. So pay attention to potential issues that could come up from ground loops. And if common mode rejection is important, isolation is going to be a key area for you to focus on. And we have the solutions for you as well. I'd like to just show you, I'll end with, where do I go for more information? Well, on our website, we have a solutions page, and the PDF is attached as a handout, and it should be hyperlinked. I hope it is. It'll take you to our solutions page, and you can see everything that we offer for our power supply measurements. There's a lot more that we offer as well, which I'll talk about in the next slide. But the key one I bolded here is the power supply measurements. This is really going to summarize everything that we talked about today. If you're working on power supplies, designing them, or you're integrating them into your system as a black box and looking downstream at your power management, these are going to give you the tools and help you understand how to make these measurements. And there's a lot of others here for switching loss, magnetic measurements, et cetera, that Satish has hit on. So I encourage you to click through these, and hopefully that will help you on your journey to debug your power supply measurements. And last, this is a very complex topic, and we had challenges to probably get this within the 50 minutes here. We talked about switch mode power supplies. We have a webinar planned in the Q3 that's going to talk about what happens after the power supply. What happens when you start converting that to DC-DC and as it gets sent out through your boards. The third webinar I plan on Q4 is going to put that all together, which is going to talk about your power distribution network. So that's going to include both your power supply and your power management. What are the problems that you're going to have, and how can we help you debug there? So I want to thank you again for your attention. My name, again, Bill Driver. Satish Kumar presented the measurements. Please feel free to reach out to us. If you have any questions, we can help you individually with your, come into your lab, et cetera, or go deeper into any of the measurements. So I'd like to turn it back over to Leon.
All right, thank you, Bill. Also, you can engage with both Electrorent and Tektronix on LinkedIn. We encourage you to follow our company pages to stay in touch. Also, for more information, you can go to electrorent.com. Bill, I think you had a couple of points you wanted to make still.
Sure, there's a lot. We kind of keep our own frequently asked questions on this topic. Two that come up, and one specifically, Satish presented harmonics. These are generally done with high accurate instruments like power analyzers and efficiency measurements as well. So Satish, how do we make that measurement? How have we changed our view and add accuracy to the harmonic measurements?
Yeah, actually, that's something a lot of people think, okay, I need to use in power analyzers because I need to go for many higher bit ADCs to see the harmonic components better. But I think the answer is, like, we can do a decent job with scopes as well. So today's scopes actually come with a 12-bit ADCs, and you can actually, if you sample at lower sample rates, you can actually go up to 16 bits as well. And you can actually see pretty good details in the spectrum view. We have in real-time spectrum analyzers in the scopes as well, and we have a very decent resolution in the spectrum domain, and which can actually see all these frequency components up to 200 harmonics as well, depending on which frequency you're looking at. So it's still possible with the scopes.
Thanks, Satish. Another one, it looks like your comments about the measurements and ripple seems to be a common one that we're making. How low of ripple measurements can we make on the power supply?
Yeah, that's again something which is depends on how which probes and which scopes you use. So we say our scopes with like 6 series is one of the best scopes which has like lowest noise in the industry. And now I would say you actually recommend using a power rail probe, which actually has got the best sensitivity, and you can actually you measure in the range of microvolts. But certain things you have to make sure when you are measuring power rails is like you need to have you want to avoid the ground loops, which are the major factors contributing to EMI, EMC effects, and getting a lot of pickups because of ground loop issues. And you also want to band limit the scope if you're looking at such particular ripple content, so that you are only able to get that in region of interest, the frequencies of interest. So I think with all these different techniques, so you should do very very low ripple measurements as well, like in the range of couple of microvolts. So that's possible.
Yeah, great points there, Satish. Definitely on the resolution side and band limiting to get the noise down. You also mentioned a probe that I didn't mention, kind of intentionally, the power rail probe, which is a specialized probe. We plan on talking more in depth about the power rail probe in the second webinar, because it talks about the power distribution in the DC to DC. So we'll hit more on that, but thanks for bringing that up.
And we hope this session provided some clear insights into simplifying your power measurements. If you'd like to take a deeper dive into specific use cases, request a demo, or schedule a technical follow-up, feel free to reach out to Tektronix or Electrorent. Thanks again, and have a great day.